what I did during my master's thesis at TUBI. So this is why it says TUBI in the corner. Even though I currently work at universities, I started like 2 weeks ago, I guess now. And I'm working here as a computer vision engineer. But before Christmas, I did like a master thesis with TUBI where we looked at using deep learning for eye tracking. Yeah, I'll try to keep it a bit short, but feel free to just like ask any questions while I'm talking related to anything. So yeah, this is like the overview. And so first, eye tracking, for those who don't know, is like the problem of taking images of someone's eyes with like an eye tracking camera. Usually have like a specialized camera with an LED in it that kind of shines a light on the eye, and then it takes a picture of the eye. And then from that picture, you try to figure out like what part of the screen the person is looking at. Usually, and yeah, this is used for kind of gaming or for disabled people who can't use their mouse like other people could. And what you would like, the typical way to achieve this, that as far as I know, all like commercial eye trackers right now use what's called more geometrical models. So you would like shine a light on the eye and then try to fit some kind of like sphere maybe to the cornea, and then try to like get the direction of the eye and intersect it with the screen and things like this, which is like works well, but it's kind of a complicated system and like lots of parts that needs to like fit together and everything. So people thought it would be interesting to see if you could like get the same kind of performance and everything with neural network. So basically, what you would do is you would take your images of the eye with either a commercial eye tracking camera, or you could try to use a normal camera. From this, you get a stream of images that you put into a convolutional neural network. You get features, and then with the features, you put them through fully connected layers, and you get like a point on the screen. That's your gaze. And usually you would train this by like minimizing the distance between the point that the person was looking at when the picture was taken and the output of the network. So yeah, maybe I should mention that for the data set, like they have people sitting by the screen and they show a point on the screen, and they tell the person like look at the point, and the point moves around a little bit. So basically, that's how we gather data. It's not maybe the most natural way to like you don't behave like naturally when you're looking at a point on a screen, but that's the best. Like, there's, as far as people know, there's no better way. Yeah, so this is an example. I think this is my supervisor at TUBI. This is like basically what the camera sees. And this is what it's. This is actually like a downscale version to fit into the network. But this is what you pass through.
Do you consider different scales?
Of
that?
Yeah, I didn't in my. I haven't looked at that, but like, I mean, it's like an interesting question, right? Whether or not how much you can scale down the image and still maintain quality. That's more for like implementation, right? So yeah, so when I came to TUBI, basically another guy was just doing up his master thesis, where he implemented this neural network for eye tracking, and you can find the full report on Viva. So basically, you like take your image, put it through the network, and he also used what's called a face mask. So you have a grid that says this is where in the image the eyes are. So yeah, maybe I should mention that. Like you of course the camera takes a full image of the whole face, but then you crop out just the eyes and put back through the network, and that's because it's too expensive to put the whole face for the image basically. But to make up for that, you also give it a mask to show this is where the cropping occurs. And something is unclear. But the focus of this work was basically to transfer learning to calibrate on specific people. So you train on a lot of people, and then when you get a specific user, you gather a bit of data from that user, and then you train the last few layers on just that person, and you get a personal eye tracking network. As far as I know, it works pretty well. But yeah, the limitation with this kind of model is what we bought in the beginning of the thesis. Is kind of what you mentioned in the last presentation, that the network takes only one frame at a time. But actually, there's a lot of temporal information in the data. Right? So say you're looking at a button on the screen, for example, in one frame, and it's pretty likely that you will be looking at a similar location in the next frame. So we would like to kind of find a way to use this. I mean, yeah, it feels like since all these images are consecutive frames, they're really similar. So there should, in theory, be a way to make use of that. So what we wanted to do is to add some kind of memory. So instead of the estimated gaze at time t, depending just on the frame at time t, you have it depend on all the past frames or a subset of the past frames. And what you can get from this is that you take multiple frames. In a sense, you want to run an optimal filter or something like this. And the idea is that you could remove things like if the classifier jitters a little bit, or you have noise. A network that looks at several frames should be able to be more effective at controlling the rest.
Well, what is a jitter or ROI?
So maybe I should mention this. It's like a technical. So ROI is region of interest. It's the term that you use in eye tracking. So you have the full image, and then the ROI is the cropped region. So it's the region of interest. And ROI jitter is that to actually find where the eyes are, you typically use a classifier to find the corners maybe of this image, and then you cut it out. But of course, there's no guarantee that the classifier will find the same location all the time, so it will always keep relevant. So maybe if the classifier jitters, you will get the jitter in the output instead. And so you suppress that. So how do you add memory to networks? You use recurrent networks. And they are most heavily used in natural language processing, I think. But there's so people use this a lot for natural language processing because there you can maybe represent your words as vectors. But for videos, it's not as clear how you're supposed to actually get recurrence, I think. So that's kind of what I started looking at. Let's see. So this is a normal recurrent network. You will recognize it if you use it before, and you can extend it to this game too. We kind of we want to do. So there are several approaches to getting memory to your network, and the first one is to take your existing network, extract features with convolution layers, and then once you extracted the features, you have some kind of recurrent connections on your features. So basically, you store between the frames. You store a vector, which is the memory, and you kind of keep track of time that way. So this is a zoomed-in version of this image. You get an input. So at each time frame, you get an input, and you calculate an output. And then for the next input, you concatenate the last output basically. And this is what is called the state of the neural network. And if you know like LSTMs, you know that there are ways that you can make this state more complicated, but it's essentially the same. So yeah, you combine these together. But the problem with this kind of fully connected recurrence, I think, is that the memory is very far away from the actual image, right? So you have your image and then you calculate features, and then in some abstract vector space, like latent space, you try to find temporal information. But there's no like guarantee that this representation is good in the time domain. So the thought is that it would be nice if there was like a way to get like memory closer to the image. So what you do then, so what you can do then is have something called convolutional RNNs. And this is where you do kind of the same thing as with the fully connected layers. You get so the green thing here would be the input image. You do a convolution on the input image, get an output, and then for the next input you concatenate the last, you can concatenate it to the next input. So your state is, instead of your state being a vector, your state is now an image with a bunch of channels. And I think what's good about this is that you can have like some really like nice features that you can learn. So for example, you can have a feature or a feature channel here in your output that detects eyes that are moving to the right. So like it will detect that in this image the eye is located at a very specific position. But in the last image it was kind of the same but a little bit to the right. And then you will have a feature that kind of detects this difference and fire on it very early. And this kind of difference, I think, is much easier to find close to the image than to get in this data space. And yeah, I think that if you look at how the brain is actually doing it, I think some of the earliest neurons after you get like light information from the brain, they will look for like very specific shapes. They will find for very specific shapes, and they will find for very specific movements. So for example, a bar that's translating to the right. And I think this is like a framework for learning that kind of picture. People have been using this. It's not like a super popular technique, but I think last year or something, NVIDIA published a paper where they use this to like get temporal consistency in reconstruction problems. So they have like, I'm not sure about the details, but they're like trying to reconstruct some 3D environment. But they notice that if you use like reconstruct one frame at a time without considering time, you get some like noise because it doesn't know how the frames are supposed to fit together. So they use this recurrent network, and they have like a regularization, I think, for like enforcing it to be similar frame after frame. So this will be like your normal encoder-decoder network, but the addition they made is that they added these basically recurrent connections in each layer that serves as a memory. So this is more like a math level. So if you know like what RNN does usually, you basically take the regular RNN and you replace the matrix multiplications with convolutions with filter kernel. So here you would have like A times the state and U times the input, but now instead you have the input image and you can convolve it with feature channels. And then you have your state, which is also basically an image with a bunch of channels. And you convolve it and you add them together. And you can do the same with LSTM. So it's basically the same. You replace you take the regular LSTM and you replace all the matrix multiplications with convolutions. frame-wise addition. Yeah.
And so you use just one filter or multiple filters? Maybe you're gonna come to this with your method, but I'm just curious about when you say you do a convolution. Is there a specific guidance on how big the filter is?
No, I mean this can be like any number of. So it's basically the regular. Think of a regular convolution layer. You have an input image, and you have a bunch of channels, and for each channel you have like detector.
Just the kernel.
Yeah, kernel is the word I was looking for. Yeah, you have like a bunch of filtered kernels, and yeah. So maybe, for example, look at this one. You say the input image is 3 channels for an image, and then you have maybe 64 channels for the state. So this will be like taking 3 channels and put out 64 channels, and this will take in 64 channels and put out 64 channels.
And did you play with the sizes of the filters?
A little bit, yeah, but not too much. I think when you're time constrained, you should spend more time on other things. It's good to nail down just one architecture.
Yeah, but you don't seem to deal with the movement, basically. So you just have a recurrent thing that you assume that things are moved, but you can move around. I don't want to estimate somehow.
Yeah, but that's the thing. These networks can actually detect this kind of movement. So if you have a network that just processes one frame at a time, then as you say, you can detect movement. But in this, so you could, for example, have like a feature, a kernel here that actually takes the difference between like the H and the X, and that's like what you get as a feature would be basically how they change. And then you have like neurons that trigger that. So you have no neuron in the network maybe that triggers for eyes that moves to, and then you can take that into account when you make the actual prediction.
Yeah. I don't know if it's kind of the same question, but so you have a memory that represents different features in the image. Are you saying that this can be kind of translated as the person or the camera moves? So that if the person or if the camera is like tilting, what's it called? It's the thing crossing a room, that this network can learn to like shift the previous features of the images and translating them as the camera moves.
Yeah, but then maybe I think it's more about like detecting the movement than
Okay. So another thing might happen.
It's like with this kind of architecture, you give the network like the ability to see differences between frames. So like in this case, if you move the camera around, a normal neural network wouldn't know that you're moving the camera around. It would just know that like this frame you look here, this frame you look here. This network would be able to like know, okay, right now the camera is moving to the right, and then maybe like that helps you to make predictions. Yeah, that makes sense. Okay. So yeah, what's the kind of technical solutions you have to solve to do this? So I think like in general, a big thing in the project was that like how do you take a network that's designed to process one frame at a time and kind of extend it to process several frames at a time. And the first thing you need to do is actually to make sure that your data set like has the right structure and information in it. So what I did is I took like, instead of each data point being one image, one data point is a sequence of images, specifically like 20 frames. So one data point is 20 frames after each other. And during these frames, like, this image is like one recording of a person looking at points on the screen. It's like when they start the point they were looking at is here, and then it moves slowly to here, and then it stays there for a few seconds, and then it moves. And while this is going on, the person is being like tracked with the camera. And I basically chopped this trajectory up into small parts, and like each part I chop out is one. Yeah, and then apart from updating data set, you need to update your loss function. So I think I did the most like simple update you can do is like basically instead of taking the average over uh, all the errors in your data set, you take the average over all the sequences. So I think important thing about training is that when I like added memory to the network, I noticed that you kind of have to pre-train it on the single frame task, at least in the case of eye tracking, because you know the network can like reasonably predict the gaze from like frame wise. So I trained it on that first, and then I use that as transfer learning to the network. If you don't do that, actually, it doesn't learn anything in these cases. And then you like go gradually up. So you start with like really short sequences of length 3, and then you go to like, 6 frame. Or that's what I did. So what the network sees is like from 3 consecutive frames to 6 frames. And I trained for 15 minutes, or more basically until it converges. Yeah. So for the architecture, this is the baseline. So CNN part, the fully connected part. This is the things put together. It basically use like extract features and then like a lot of fully connected layers, and then you get XY coordinate output. And this is the error used for reference. The average, like so this is in millimeters actually, so it's like kind of
Accuracy.
So accuracy is so let me read. I can get this right. Accuracy is how spread out the guesses are. The precision is how accurate you are. So basically, accuracy is like how good is the mean of your estimate. The precision is what's the standard deviation of your estimate.
Can I ask about the frequency of images? Do you use the same frequency as the standard eye tracking camera? What is this?
Yeah, so I use 30 frames per second. And I think it's like the camera takes like one image and then another image. So actually, the real camera is I think 60 hertz. But because the two images are different, because they use different lighting for the two different images, I make it simpler. I use only 30 frames per second. But the network can actually run like in real time, 30 frames per second when you use it. I'm not sure about 60, but maybe. And this is not even on a GPU, they're on a real time 4-core CPU. But yeah, so the first kind of experiment is to add memory to use the fully connected part. So I took a few of the last kind of fully connected layers and I added regular RNN cells. And these are actually, in this experiment, it's not LSTMs, it's just regular RNN cells. And what you see there is that you get like actually a little worse than the baseline. So it looks like if you just have recurrent networks, at least when I trained it on the feature layers, you're more like confusing the network basically. So I went on to the second part, which is to add convolutions in or recurrence in the convolution layers. And there you start getting some improvements. So I can improve it by a few millimeters from doing this. From 47 to 43. This is like I should mention. The networks are trained, so they're trained on sequences of length 6, but they're tested on sequences of length 20. So they have to like be able to generalize a little bit to have good scores in these data. But so yeah, the last experiment or these are actually two experiments. It's to have the recurrence in both the convolution part and the fully connected part. And I did both with regular RNA cells here and stem cells. And what I got at least is that if you have LSTMs on the convolution layers and regular RNNs on the feature layers, then you get like the best results basically that I could find. But if you have LSTM on the convolution and LSTM on the feature layers, then you can't really generalize. We get and you can see this a bit more clearly in this graph, I think. So this is like a graph of the error of the network with respect to time. So you show, here on 0, the network has seen no frames, and then you give it a frame, and you see how good it is. Just like one frame, it has no history or anything. So, and then you like, as you give it more frames, in theory, if the memory of the network works like it should, then the more frames you see, the better the prediction should be. So like the more information you have to like make a good guess of the position of the eye. But as you can see, not all networks actually achieve this. So the blue line here is the baseline. So because the baseline is just a network that's looking at one frame at a time, the error doesn't really change over time. It's just like a noisy straight line. But when you use so for the two like good networks, the one with recurrence in the convolution layers, they both like start off, or at least the red one starts off really bad because I was ignoring the first 2 frames in the training. But then as it sees more frames, it actually gets a little better over time.
So on average, they are 4 centimeters away from the truth.
Yeah. And so let's see. But yeah, also from this one you can see that you can't just add like recurrent connections anywhere and you can expect it to be good. So like this one, the purple one, it actually starts off really bad, then it gets kind of good during the first few frames. And this like that bars, they show the training time. So what the network saw during training is like sequences of like 2 and 6. So like yeah, they see I gave it 6 frames and it has to make a prediction on each of the frames. But when you train it with LSTMs in the feature layers, then as you show it more than 6 frames, like up to 20, it actually gets worse with time. So that kind of indicates that the state is stuck in some like weird space where it actually thinks it's doing something completely different. Yeah.
You said 4 centimeters, so it's lost the root mean squared.
So I have to let's see that. So it's like the average distance between the. So xi would be the true point where the person was supposed to look, and x hat is the estimate. And you just like take the average. And for sequences, you take the average of several sequences. But I guess like the thing here is that you don't start at finding 0, you start at.
So, but if you take the square root of 40, then you get the average standard deviation pretty much.
Yeah.
Because this is square.
Oh yeah, that's true. So it's not actually 4 centimeters. But yeah, I'm not super sure what the actual dimensions here actually, because it's kind of. I'm not sure if we use some kind of normalization of the output or something like this. But yes, this is like a example output. So green is the ground truth, and red is when you use like the memory, and blue is when you don't. So you see that in some parts, especially when the gaze is standing still, like the blue one is jumping around, when the red one is usually at least a bit more still. And like a nice thing I think with having recurrence in the convolution layers is that you get like features that depend on the time. So instead of your state being just a vector in some space, like the states are actually images. You can see a lot of these features are looking for eyes, I think. Most of them fire on the eyes, some of them are like that looks like that's this one triggers a lot in the nose or something. So yeah, I think that's pretty much it. In summary, like what I kind of come to the conclusion for, I think, is that like you can improve performance somewhat with this kind of recurrent connections. But the big problem is that you run into like, more architectural problems with your training. So this problem where instead of having one image as a data point, you have 6 images or even more. We're kind of limited in that way. So I think if with like more time and GPU power, I think these kind of methods can gain even more advantages. I feel like that was like one of the main limitations is that you can train it for I can't really wait to train it for 7 days. Another nice thing is that you can use when you have a recurrent model, you can actually use it for prediction. So like in theory, you could try to predict where the person is going to in 1 second or something like this. It's nice, I think. With like pretty minimal like coding channels. So yeah, I think that's it. I have some code examples, not for eye tracking, but for there's a data set called moving MNIST where there's like MNIST digits bouncing around in a box basically, and you try to predict where they're gonna go. And you can do this with this recurrent model. If you wanna, yeah, that's it.
What's more expensive was doing inference, the one with memory without. So what one is it?
So definitely, it's a trade-off. So I mean, when you have memory, of course, it's extra channels. So you basically get more convolutions to compute, but you can also like trade off. So you can remove like half of your channels in your convolution and replace them with feature channels, and basically then it's no difference. But yeah, that's something you have to figure out. But in my case, it was more computations because
You get the same architecture.
yeah. Or actually, I did a thing where I replaced, so the number of the like effective number of weights in both models is the same. Yeah, because otherwise you could argue that like just you get the performance increase just by because it's more weights.
Have you considered the factor of like rotation of head, like if you just for the testing take one sequence and just rotate it and input it?
No, not really. I think that's a bit more difficult with. You mean like data augmentation?
Yeah. Or like in the testing, just to rotate and see whether it works when it's out of scope of the data space.
I think this is like, especially with eye tracking, is a bit difficult because you kind of rotate the image, I guess, but you don't really know how that translates to like a change in the gaze scope. But I think one of the like main disadvantages of this data set is that like when it was gathered, they like tell the person to sit like exactly still in a chair, like with their face like facing forward and look at the point. But when someone uses a computer normally, they would probably like move around a bit. So I think if I showed those kind of images to my network that was trained in people sitting still, it would probably freak out whatever because it sees variations that it's never been trained on.
It's like you need just have to align the face according to what you want.
Yeah. But still, like, even if you align the face,
Yeah.
then you lose it, because like if
Yeah.
you just sit here and if you sit 1 meter down, it looks the same in the image, but the gaze is different. It's a bit tricky also. I think the best like solution would be to get it better.
Or attach an eye tracker.
Yeah,
Always.
yeah. It's I think nobody has that.
It's very big.
Yeah.
You want to bring in dancing, right?
Yeah, I guess they have a consistency. You have to see with that when it's done. Yeah. Any other questions? Okay, then I guess we'll take a break for the next talk.
Det var ju 25 nice att prata lite.